Yo, what's up, guys? Welcome back. Episode 53, I think. Just got done playing tennis, so probably gonna jump on and just do a couple questions. But yeah, probably again, just probably normal day, a few questions, and we'll probably call it that. Um, yeah, little Saturday grind session. Got to keep being consistent, hopefully. So, yeah, we'll do a couple questions there. Trying to think. What should we do? Let's take a look at Pokemon of the day. That's what I was trying to think. My brain wasn't working. We got a Persian, the evolution of Meowth. Let's take a look, shall we? Kind of same thing as Meowth, pretty much. There's our Pokemon sound of the day. Gotta respond to this really quick. Okay, sorry. I have to respond to this really quick. What should we do? I'm trying to think. Let's take a look. Yeah, I don't know. Let's do a sliding window problem. I kind of want to do like a problem of each. So let's do like a. I mean, bro, I know I've done all these already. Let's do a sliding window problem first. Actually, let's check our problem of the day. How about we? Oh, jeez, man. Let's take a look. Oh, no, we were gonna do this problem yesterday. I forgot. Let's do this problem. Little hard problem. Run a pre-order depth test, set D first in the root of a trinary tree at each node of this special. We output D dash is where D is the depth of this node. Then we put the value of this node. If the node or node D is the depth of its child, D plus 1, the depth of the root is node 0. Okay, so I think here this is definitely a BFS problem, only because we're traversing by the level. So obviously starting here, like we increase the level every time we traverse to the new values. So I think the way we're going to do this is we're going to do... Gosh, man, how do you... I always forget. From collections, import. Let's do the queue. So... From collections, import DQ, right? I guess Q is equal to DQ. We put in our root, right? Traversal string. Oh, fuck. Okay. Sorry to curse. We're going the other way. So, okay. So we're traversing the string and then we're making the tree. I think. Okay. I understand. Recover a tree from a pre-order traversal. We run a pre-order depth first search DFS on the root of a binary tree. At each node in the traversal, we output d dashes where d is the depth of this node. Then we output the value of this node. If the depth of the node d, the depth of its immediate child is d plus 1. The depth of the root node is 0. If a node has one child, then the child is guaranteed to be the left child. Node has one child, and the child is guaranteed to be the left child. Okay. Oh, okay, so DFS here, so we start at 1, we go 2, 3, then... Okay, I have to try and think like kind of how this works. 3, then we go, so 3 is 2, then we have 4, then we have 5, because that'll be the right of 1, 2, would be the right of 5, 6, and then 7. Okay, then we want to output the root of the binary tree. I think, yeah, return its root. Okay, so we don't need a queue to solve this, right? Now I'm trying to think, how can we solve this problem? Well, the thing is, can we... What I'm trying to think is that, can we skip? Is there a... I'm trying to think, is there a way that we can skip here? So when I say that, is that, can we just traverse the string in a kind of DFS-like way and skip the hyphens, technically? Because DFS always, you know, goes like this, you know, always goes left, so probably not though. Tree, depth first search, binary tree. Do an iterative depth first search, passing dashes from the string to inform you how to link the nodes together. If we're doing an iterative depth first search, let's just start with that root node. And while the stack is not empty, one 401. I'm just kind of not sure the way to approach this problem, to be honest. Like, I'm really not sure. An iterative DFS-based approach. Passing dashes from the string to inform you how to link the nodes together. So you do use the dashes. Yeah, I'm not sure. I'm going to need to get another hint. I'm not sure kind of how to do this. 728. Cover a tree from post order traversal. Give me. Left, right, root. Yeah, but I'm not sure. Why is there a null here? I don't understand why there's a null here. 140, 349. Yeah, you know, I'm not sure. Let's check this from Leetcode. I'm curious, like.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem, recover a tree from pre-order traversal. It's actually a pretty interesting problem, especially for a hard one. I think it's not too crazy. And I'm not going to lie, today is kind of one of those days for me. I'm a little bit tired, but I mean, who isn't? So I'll still try to make the best video possible. And by the way, how's the mustache coming in? So the idea behind the problem is similar to another variation of this where we're actually given like a pre-order and like in-order traversal, and then we have to kind of reconstruct a binary tree. But I think that's like a binary search tree. This problem is a little bit different. So in case you've solved that problem before, just kind of keep that in mind. This one is different. So we are given a pre-order traversal of a binary tree, not a binary search tree. So you notice that here. There's no search property. It's not like every value on the left is going to be less than the value at the root. And the form that we're given this pre-order traversal is pretty interesting. So see it over here. I'll go through what they mean by this because that's really what the whole problem is about. So in this example here, notice that we have a 1. After that, we have a single dash and then a 2. And then after that, we have 2 dashes and then a 3. Now, there's not actually any spaces in the string like I've drawn them, but I'm drawing the spaces just to make it more clear what we are given. And then we are given 2 dashes and a 4, and I'll keep drawing it down here. And then we're given a single dash and a 5, couple dashes with a 6, couple dashes with a 7. Again, this is given in the form of a single string, no spaces. And what this represents is, first of all, it's straightforward to recognize that the numbers themselves represent the values of each node. And this example is pretty simple, but recognize that there could be multi-digit values. That's one thing you have to recognize. So this could have been a 20 or, 222, something like that. I think it's bounded by like 1,000, so that's the max value any node will have. We won't have any more than 1,000 different nodes. But notice that we're also given these dashes, and these dashes are going to be very useful for us. each dash will tell us what the depth of that node is. So however many dashes come before a given value will tell us the depth of that node. This is very useful for us because it tells us that, first of all, like the first value, it's just a 1. There weren't any dashes that came before it. So we know for sure that this is going to be the root. But actually, we didn't need the dashes to tell us that that was going to be the root. We know that the way pre-order traversal works, I mean, if you're solving this hard problem, I hope you do know how pre-order traversal works. If you don't, consider checking out some courses on Leetcode.io. I'll try to briefly explain it right now. But basically, it means that like the way we would traverse this tree is first we traverse the root, then we would recursively run pre-order traversal on the left subtree, and then after we're done with that entire tree, we would run pre-order traversal on the right subtree. So recursively, this is how it's going to work. We're on the left side. We start with the root. We do that first. And then we go to the left side of that. And then we see 3. We do that first. So you can see that the order that we were given these in, 1, 2, 3, matches that of the pre-order traversal. And after that, we do 4. And then we're done with the left side. So then we move to the right side, 5, and then 6, and then 7. So that matches the input order. So far, everything seems very simple. It seems like everything is given to us. It doesn't seem so bad. And it actually isn't, but there are a couple things you do have to notice. Why would they be giving us these dashes in the first place? There must be some level of ambiguity. From just a single pre-order traversal, it's probably not going to be enough for us to take this traversal and then rebuild the tree. That's what we're ultimately trying to do, rebuild a binary tree and then return the root of that tree. Again, these dashes will tell us the level of each node. So we see that, of course, 1 will be the root. This will go on the second level. The second level can only have up to 2 nodes anyway. So we see that this is a node that will go on the second level. And of course, this is a node that will go on the second level as well. And then we can see all 4 of these nodes will go on the 4th level. Of course, the dashes alone do not give us enough information on where to place the nodes. So we need to use a combination of these dashes as well as the fact that this order is a pre-order traversal to decide the correct positions. But isn't it possible that even with that information, there could still be some level of ambiguity? And actually, it is. Let me kind of just give you a very, very simple example. What about this? Okay, this tells me that I have 1 as my root. This tells me that 1 has to have a child of 2. But I don't know if it's going to be the left child or the right child, right? You have no idea. Pre-order traversal would... traverse this tree here, which it looks like this, the exact same way as it would traverse this tree where we had everything on the right side. So how do we know? Well, they actually make it very easy for us. They literally just tell us if a node has only 1 child, that child is guaranteed to be the left child. So we can definitely use that information to our advantage. That would make this very clearly to be this tree. It would look like this. 1 is going to have a child of 2, a left child. And then for this node, 3, I mean, there's nowhere to put it on the right side. It has to go over here. And 2, again, we're not going to make it a right child of 2. It only has 1 child, so we would make it a left child of 2. So that's more or less enough information to be able to solve the problem. These are all the observations that you need to make. Now, the first thing I thought of after processing all of this information was maybe that we could just do some kind of level order traversal. That might be like the easiest way, because if I could just go through and parse the input string and then determine, okay, we're going to have 1 at this level, we're going to have 2 and 5 at this level, and 3 and 6 on this level, and 4 and 7 on this level, then maybe I can somehow just put the nodes together. And maybe I can do some kind of bias where then I can choose the nodes to go on the left side. Well, that would be ignoring the fact that the order of these elements was, again, the pre-order traversal. So that's why it's not going to work. How do you know if 7 should be a left child of 6, and how do you know that 7 shouldn't just be a right child of 3? Our level order traversal would not give us enough information to do that. And so that's kind of when I realized that probably the way to solve this problem is to go through the input. At least one possible way that I thought of was, okay, I know that tree traversals can be kind of simulated with a stack. Pre-order traversal should be doable with that. And so somehow we can scan through the input. And I'll be honest, my thought process for this was just to try this and just figure out the little details as I went. And it just turned out that my code that I just kind of sloppily threw together, it did pass, it did work, and it was actually the optimal linear time solution. So that's kind of what I mean by when I say this is one of those days where it's hard for me to really put a lot of effort into think about it from your guys' shoes if you were not able to kind of arrive at this solution. But I think this solution isn't super crazy for a hard problem. As I kind of just try it out, let's just try out the stack solution, figure out the little things as we go, and hopefully it'll make sense to you. I'm going to try this on the second example because I think it's a bit more difficult. So knowing what we know, this is why the stack solution seemed appealing to me, because we could try something like this where we parse the input. We see the first number, and we see that we haven't seen any dashes before it. We can just have a single variable to keep track of how many dashes we've seen as we parse the string. That's really not the hard part of this problem. Like so far we've seen 0 dashes, so this is our node. This is the value, and there could be multiple digits, so we might keep reading them until we no longer see any digits connected to this. It's just a 1 right now, so it's pretty simple. So we have a 1. We can create a tree node of 1, and we can add it to our stack. So I'll just draw it like this, like as a node. And then we'll keep parsing the string. Now we see a dash, there's a single dash, so we'll keep track of that. We've seen 1 dash so far. And then we see another number, it's 2. So that's kind of always going to be the case. I mean, can you imagine a tree where with the rules that they gave us, where we're going to have a node and it's not going to have a left child? I mean, that has to happen. Like, that's guaranteed to happen if we have 2 nodes in the tree. We're never going to have a tree that looks just like this. So far, so good. We take now the next node that we've seen, 2. There was 1 dash that came before it, so we know that this node is on the next level, and we see that, like our previous node, which was the root, it does not already have a left child, and thus we're going to take 2 and add it to the stack, but we're also going to have ended up connecting this like with the 2 node. So just keep that in mind. Even though I'm just drawing the stack, we are sort of building the tree as we go as well. I'm going to keep parsing, and now is when things actually get interesting. Now is when there could be a junction in our solution. There could be 2 different possibilities. One is the possibility that occurs right now. We see 2 dashes and a 3. So this is where keeping track of the dashes is actually going to be useful. So we've seen 2 dashes, and then the value for our node is 3. We will, of course, create a node for 3. And the fact that this node is on the next level means we're going to take the node and now add it to the stack. And again, with the previous node that was on the stack, we're going to connect its left pointer to 3. So that was one possibility. Can you please take a second to tell me what the other possibility would be? This is a hard problem. You should be able to figure it out. What would the other possibility have been? Well, if this node 2 did not have a left child, well, then it's guaranteed to not have a right child either. So again, you tell me, which other place could we have possibly inserted a node? If not here or here, then the only place would have been here. So what if there was only 1 dash that came before the 3 and not 2? How would our solution have been different? Try to answer it on your own, but if not, I'll answer it for you. If we had just 1 dash and the value was 3, our solution would have to have been different. We would have then saw that this node has to go on the second level. It could not be connected to this node. It would have had to be connected to the root node. Now, how is that going to work with our stack-based solution? What's our stack going to do? Well, isn't it true that our stack should kind of tell us like a path? It should tell us how deep we are. I mean, that's how stacks work. That's how recursive stacks work as well. So if you're doing this recursively, the recursion is going to be doing the exact same thing. It's going to tell you how deep you are in the tree. So really, we can use the length of our stack to sort of tell us the depth. And we can compare the depth with the number of dashes, because we know the number of dashes basically tells us the depth of the current node that we're trying to insert. So if I see that my depth, my number of dashes, is equal to 1, then I can say keep popping from the stack while the length of the stack is greater than the number of dashes keep popping from the stack. So in this case, we're only going to need to pop once. We pop this guy, and then we're good. Now the number of dashes matches the number of nodes in our stack, and that's good because now we can take the next node, 3, push it to the stack, and then we'll see that 1 already has a left child, so let's connect its right pointer to 3. So that's more or less how to solve the problem. I think the rest of the things are just going to be like implementation details in the code. You can do those many different ways. I'll show you one way to do it. But just to kind of run through the rest of this example, so let's just run through like the original example. So we saw that we had 2, and then we had 3, which was at the next level. So 3 then would have just been pushed to the stack, and then we would have connected the pointer as well, and then we would have kept going. We see 3 dashes and then the 4, so we see that the length of the stack is not greater than the number of dashes of the current node, which is 4, so it's fine. We don't have to pop anything, just add 4 once again, and of course connect the left pointer of the previous node that's on the stack first. The last node that was on the stack is going to be connected to the current node. So now it's going to get more interesting. Now we see 1 dash and then the 5, so dash 5. Now we definitely need to pop from the stack. Keep popping from the stack while the length of the stack is greater than the number of dashes. So this time we will have to pop 3 times from the stack. That's basically telling us that now we've gone as far deep as we can, and we just want to like pop, 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 and come back to the root. So now we can start filling in the right side. Now, had this been like a double dash 5, then we would have just needed to pop twice because we popped this and we pop this, and the double dash tells us that now this node is going to be inserted over here. And the reason for that is because it was a pre-order traversal. Remember, like this input was pre-order. We're using the fact that it's a pre-order traversal and the fact that we're always inserting left nodes first, and the fact that the dashes tell us the level of each node. We're combining all of these facts to arrive at a cohesive solution. So that's kind of like my thought process, at least. And now that we've popped these 3, we will add 5, we will connect the right pointer, and then we'll keep going. Now we see 2 dashes and a 6, so that's fine. The length of this is not greater than the number of dashes, so go ahead and insert 6, and this time 6 should be the left child of 5, because 5 does not have a left child, so it makes sense. If you see the picture here, I'm just kind of filling it in like this now. And lastly, we'll see 3 dashes and a 7. So there's 3 nodes on the stack. No need to pop anything. Go ahead and add 7 and connect the left pointer just like that. And at this point, we're done. So we've built the tree. How exactly do we identify the root and return the root? Well, if you notice the way like this logic is working, we're never going to end up popping the root from the stack. So we can always just return the first node that we added to the stack. The stack is going to be basically an array. We can just index it to get that value and just return that. So this way, I believe this solution is linear time. I don't know exactly if I'm doing anything fancy with like the string parsing in my solution, but I don't think I am. And I think it is a linear time solution for the stack. Even if you're not counting the space that's occupied by the result of the tree, the stack still takes space. So if you want to see my super authentic thought process, this was it. This was my solution that I just kind of threw together. So let's code it up now. Just a couple of variables I'm going to keep track of. The number of dashes, I'm just going to call that dash, or I guess plural is fine. And really, this is going to tell us the depth of a given node, and we're going to have the stack, which is going to be an array, and we're going to have our variable I, which is going to tell us what index we're at in the input string that we're trying to parse. So I'm going to do this while I is less than the length of the input. I'm going to check a couple things. I'm going to check if the traversal, the character is equal to the dash, then just go ahead and increment the number of dashes and increment I. Otherwise, we can do this. We know the character is a number, so we want to just get all the characters, all the digits of that number. So I'm going to have a separate pointer, which I'm going to say j is equal to I, while j is in bounds. And the character is not a digit, or rather it's not a dash, so that means it is a digit. We will be incrementing our pointer, j. So Once this loop stops, either we've reached the end of the input string or we've reached a dash. Either way, we want to just get all the characters from the I pointer to the J pointer and get the digit that represents. So we can get the substring by slicing like this in Python from I to J. J is non-inclusive. Convert that string into a number like this with Python, and then we'll call that our value. And this value we want to use to create a node. We can call the tree node constructor that they've kind of given us the definition for up above, just passing in the value. And now is where things get tricky. If you're new to iteratively implementing something like this, it might take you some trial and error. I think I actually had like 1 or 2 bugs when I was implementing this. But the first thing to do is recognize we want to add this node to the stack, but we don't know which position to add it to. And we also want to connect this node to possibly the previous node. So let's do this. While the length of the stack is greater than the number of dashes, we might need to pop from the stack. So we'll just do stack.pop. After we've popped all the necessary nodes, we maybe need to connect this node to like its parent. Unless, of course, this node is the root. I think this is where I actually had the bug. I initially tried something like this where I said, if not stack -1.left, then do this. Stack of -1.left is equal to the node that we just created. Now, what does this code mean? It's saying the last node that we added to the array, that's what -1 means in Python. If the left node or the left pointer is null, that's what the not means, then take the left pointer and assign it to the current node that we just created. But what if the stack is empty? That's what I did not account for, so we can actually fix that pretty easily like this, stack and that. Now, the other case is else if the stack is non-empty, then we just want to do this, except we want to do it on the right side. So you can just change this to the right pointer. Now, after we've done that, we do have to make sure that we take the current node and add it to the stack. So we can do this. And this will happen regardless of this executed or not, because we might be adding the root node to the stack. And also, just some like basic things to not forget are to update our I pointer. Since we iterated through all the digits, we might as well move I to be J now. And we can also reset the number of dashes back down to 0, because now we've just processed the current integer, the current node. So we can reset this to 0, so then we can recompute it up here. And I believe this is actually it. I was surprised that this worked, but I do think it does. We can return stack at 0. And unless there's some bugs or typos here, I will go ahead and give this code a run. And yeah, you can see here on the left side, it works. It's pretty efficient. If you found this helpful, check out Leetcode.io for a lot more. Thanks for watching, and I'll
Yeah, wow, what a solution. Sorry, I was so locked into to listening to that. I actually got kind of tired a little bit, not gonna lie. Okay, let's take a look. Obviously, we want to make as ashes, right? Ashes equal to 0. Create a stack, right? I want to create a variable I so we can iterate. Well, I is less than the length of the traversal. So we loop through each value. We want to check well. What number? What are we looking for here? Well, if I think, okay, let's do, okay, what do we do if it equals a dash? So let's say if traversal equals dash, then what do we want to do, right? We want to add 1 to dashes. I think that's about it, right? Oh yeah, an increment. Whoops. Thinking we were using a for loop. You want an increment, right? Else, well, we want to get are you doing else here? Yeah, okay. What we want to do, it's number, we need to get all the numbers, so we need to make a new pointer, right? And then we need to do, well, while traversal I does not equal a dash, I guess at this point it'll be J, I think. Dash, then we want to do num is equal to I to J. While traversal J does not equal dash. We need to increment though. Gonna keep recomputing this, so. Oh, we need to stay in balance. Traversal and traversal. That's going to recompute if we do that. So that we want to do here. Nums is equal to ij. That's how you do it in string manipulation, right? Yeah. So this is slicing. I'm going to change this well to an integer. So we cast it into an integer. And then what do we do from here? We this is the hard part here. We need to check, well, we get our num here, right? Checking those dashes, right? So you check, well, if dashes is equal to the length of equal to the length of the stack, then we can just, I'm not sure actually. No, that's not how you do it. If stack and not stack minus 1 dot left. if there's something in the stack and the stack, top of the stack is equal to null, then we just do, well, stack minus 1 dot left is equal to nums. Well, we've got tree node nums. Change into node. How about that? Let's change this to num. Okay. Check left first, right? And then we check right. Check right. If stack, right? Then stack minus 1 dot right is equal to none. Then we need to stack dot append num. And then dash is equal to 0. We want to return the root node. But you do check while the length of the stack is greater than dashes, then we need to hop everything. Right. Oh. What is this about? What am I doing wrong here? Oh. Whoops. Oh, I think we need to make I equal to J. Oh, fuck. Whoops. Oh my gosh, dude. We're appending the node, bro. Oh my gosh. Oops. J's less than like the traversal J just. Oh my god, dude. We're assigning it to node, not node. Bro, there's so many errors here, dude. Like, right, turn stack. I don't understand
The
what's
correct
wrong.
node. So we can reset this to 0, so then we can recompute it up here. And I believe this is actually it. I was surprised that this worked, but I do think it does. We can return
Oh,
stack.
bro. So stupid, dude. That's why. Literally noticed that it was returned was indented on. Bro. So stupid. That was an interesting problem. For sure. I mean, bro, there's no way I would have got that like that. I don't know. Like, there's no way I could think about that. You know, to be honest, I kind of did think about that, but I didn't really know how to execute it. Like, you know, it's okay. Yeah, frustrating, but it's okay. Let's do a simple stack problem. I mean, hash my problem. Then I'm probably gonna I'm gonna take a nap because I'm absolutely exhausted. Let's do bulls and cows. Ugh, you play with bulls and cows game with your friend, dude. Seems like too much. Think about right now, to be honest. Number of bulls, which are digits in the guess. Okay, we're gonna do it. Let's take a look at it. You are playing the bulls and cows game with your friend. You write down a secret number and ask your friend to guess what the number is. When your friend makes a guess, you provide a hint with the following info: the number of bulls, which are digits in the guess that are in the correct position. Number of cows, which are digits in the guess that. Bro, what? Number of bulls, which are digits in the guess that are in the correct position. Okay, so the guess is 17. Okay, so 8 would be a bull in this case, right? We got A. Why is it B? Bro, I don't understand. Two bulls and shit. Look at this guy, bro. Bro, I just don't understand this question. Like, I don't understand how you get the output. Oh, okay. Okay. I should have read this line. The hint should be formatted as X, A, Y, B, where X is the number of bulls and Y is the number of cows. Note that both secret and guess may contain duplicate digits. Okay. So bull is if it's in the right position, right? So we got an 8 and an 8. Okay. So that's why we print 1, right? We got 3 Y's here because we got 0, 7, and 1. Okay. I understand. So 1A, 3B. Okay. The guess is 1, 1, 2, 3. So the guess is 0, 1, 1, and the secret is 1, 1, 2, 3. So then we output, well, we got, 1A here, and 1B, That's it. Okay. Okay, I think I understand. Okay. So this isn't too bad of a problem, I don't think. Hopefully. Constraint secret and guess consists of digits only. Secret and length is equal to guess length. Okay, so I'm trying to think what we can use here. Well, I'm trying to think. We have one here. Can we use the hash? I mean, I'm pretty sure it's a hash map. To solve this, obviously, I mean, it's a hash map question, but if we have one here and one here. I'm so gassy, bro. Whew. One and one. Can we loop? We can loop over and just compare the values, right? Okay. Let's do. I'm just gonna count the bulls, right? Bulls and cows, right? So to find the bulls, I think we just got to loop over secret, right? We got to loop over, I mean, since they're the same length, right? We can loop over both and just check, well, if any of them are the same value. And if one of them is the same value, then we could just increment the bulls. Okay, so that's the way I'm going to find the bulls. So let's find bulls, right? We're going to loop over, fine. I mean, really, do we need the index for I in... Okay, for I in range, length, secret, right? We check, well, if secret I is equal to guess I, then we can just increment bulls. Alright. I think that should easily find the bulls. I'm pretty confident. Yeah. Okay. Right. So now how do we find... So now how can we find the key? Well, I think we're going to need a dictionary for sure on this, right? Okay. Else we can check, well, if secret I guess we can use a set here, actually, I feel like. because we can. Right, we can use a hashy here because if we have the dictionary, right, we can just add all the numbers that are in hashy, right? So if we see 1 and then 7, like we add them in there, but then if it's, oh wait, would that work? Would that work? I actually don't know. Well, if we live through, if they're not equal to each other, then we do 1 and 7. We add that to the hash map, but then there could be two 7s. Like here, there could be 2 1s, or 3 1s in this case. So. Could we hold 2 keys here? Well, maybe we do use a dictionary. I feel like. Now we got to count all the values. So, well, if hashy. Do we compare the hash maps or do we use one? I feel like we have to compare, like. Not in hashy. Yeah, I think we gotta make 2 separate hash maps. Secret I not in hashy. Not inside my dictionary. Let's go. Else secret minus code secret I equal 1. Alright. Another statement here we do, well, if guess I'm in my dictionary minus secret yes I oh shit, whoops, again yes I plus equal 1 else okay secret I is equal to 1, right? brown cows. Okay, let's print out our two is equal to this. Okay, this needs to go my deck two, my deck two. Yeah. Oh my gosh, dude. Print print two. Spelled secret wrong? What is wrong with this? Key error 1. What is wrong here? I don't know. Key error. Oh, gotta do it the other way around. Bro. What? Bro, I don't understand. Like, what is going on here? Okay, I don't even know what I did wrong, bro. Like, what? Oh, okay. Alright. Okay, whatever. So we got, okay, so we got one. Well, the first one should be secret. Okay. One zero seven, right? 7 1 0 1. Okay. So somehow we got to compare now. We got to do well. How can we compare here between the hashes? How can we compare? Well, if one is the key function to compare So I guess we would do for key in my dictionary. If key in my underscore dictionary 2, then we take the min, right? So we would do min value is equal to the min key, and we would add that to bulls and cows. We'd add that to cows, so we do, well, cows plus or equal to min value. And then I think we return, well, what would we return? We'd return like turn the string turn cows plus a plus is the cows not the bulls plus a plus cows plus b. Bro, I don't even know if this works in Python. I don't even know. Type error, okay. Oh, okay, we need to cast this into a string. Okay, that's fine. String bulls plus cows. Oh shit, we need a string here. Here we go. Let's go. Nice. Let's see some other solutions. One pause Java solution. Yeah. Kind of same way. Not too bad of a problem. Not too bad. Let's post a solution. Simple Python solution. Nice, dude. Alright, we're gonna end it here. Appreciate you guys watching. I will see you tomorrow.